Now, let us start looking into a new chapter, that is Laplace transforms. In one of the previous chapters, we looked into frequency domain representation of signals, as a part of which we looked into Fourier series, which is for continuous time periodic signals, discrete Fourier series, which is for discrete time periodic signals, CTFT, which is for continuous time non-periodic signals, and DTFT, which is for discrete time non-periodic signals. Out of these four frequency representations, we know that Fourier series and CTFT are for continuous time signals. Now we will look into another frequency representation for the continuous time signals. Please note that the frequency representation that we would be looking into is Laplace transform. It is a generalized frequency representation of continuous time domain signals. So we can say that continuous time Fourier transform is a special case of Laplace transforms. So now we will look into the definition of the Laplace transforms. Given any continuous time signal f of t, Laplace transform of f of t is given as integral 0 to infinity e power minus st f of t dt. This is the analysis equation which would be used to find the Laplace transform of f of t. Please note that the equation we have written is called one-sided or unilateral Laplace transform. It means that it can be applied for the signals which have the property that f of t is equal to 0 for t less than 0. If this property is satisfied, we call the signal as one-sided or unilateral signal, and the Laplace transform of f of t in this case is one-sided or unilateral Laplace transform. If the signal is two-sided, then we can find the Laplace transform of the signal using the formula Laplace transform of f of t is equal to integral minus infinity to plus infinity e power minus st f of t dt. Please note that the analysis equation that we have written now is called bilateral Laplace transform. As a part of the definition of the Laplace transform, we looked into the analysis equations of the same if the signal is one-sided and also if the signal is two-sided. Now we will look into some of the important properties of the Laplace transform. Before looking into the properties of the same, please note that if there is a signal f of t, its Laplace transform is denoted by f of s. So f of s is equal to Laplace transform of f of t. So let us consider two signals f1 of t and f2 of t, which have the Laplace transforms as f1 of s and f2 of s. Please note that f1 of s is equal to Laplace transform of f1 of t and f2 of s is equal to Laplace transform of f2 of t. Also please note that as a part of the current chapter, also please note that in the current chapter we will be mainly looking into unilateral Laplace transform by default. Means we will be considering only the one-sided signals. The first property that we would be looking into is called homogeneity, as per which if k is a constant, Laplace transform of k into f of t can be written as k multiplied by Laplace transform of f of t. So this is equal to k into f of s. Now the second property that we would be considering is called superposition. That is Laplace transform of a into f1 of t plus b into f2 of t is equal to a into f1 of s plus b into f2 of s. Here please note that the constant a comma b belong to the real domain. We will be looking into another property of Laplace transform that is called frequency shift. That is Laplace transform of e power minus at multiplied by f of t can be written as f of s plus a. Let us try to prove the same. We know that Laplace transform of any function can be written as integral 0 to infinity that function, that is e power minus at f of t multiplied by e power minus st dt. This is equal to integral 0 to infinity f of t multiplied by e power of minus of s plus a t dt. We know that this is equal to f of s plus a. This is because in the analysis equation of Laplace transform, the s is replaced by s plus a. So this integral term would be equal to f of s plus a. From this we can say that Laplace transform of e power minus at f of t is equal to f of s plus a. Also similarly, we can prove that Laplace transform of e power at f of t is equal to f of s minus a. Now let us consider another property that is called time shift, as per which Laplace transform of f of t minus t naught, that is equal to e power minus st naught multiplied by f of s. Please note that f of t minus t naught is delayed version of f of t by t naught. So this can be proved by using the analysis formula of the Laplace transform as shown, that is integral 0 to infinity e power minus st f of t minus t naught dt. This is equal to, substitute t minus t naught is equal to tau. So from this t is equal to tau plus t naught. Also when t is equal to 0, tau is equal to minus t naught. When t tends to infinity, tau is equal to, sorry, tau also tends to infinity. From this we can write the given integral as integral 0 to minus t naught, sorry, integral minus t naught to infinity e power minus s multiplied by tau plus t naught multiplied by f of tau d tau, because dt is equal to d tau. From this we can simplify the integral as e power minus st naught multiplied by integral 0 to infinity e power minus s tau f of tau d tau. Please note that we have made the starting point of the integral as 0 because of the reason that f of t is a one-sided signal. From this we can see that the given integral is equal to f of s. So this boils down to e power minus st naught multiplied by f of s. So from this we can say that Laplace transform of f of t minus t naught is equal to e power minus st naught multiplied by f of s. Now let us consider another property which is related to differentiation in time domain, as per which Laplace transform of d by dt of f of t is equal to s into f of s minus f of 0. Please note that here f of 0 is value of f of t at t is equal to 0. So from this we can say that if f of 0 is equal to 0, then we can say that differentiation in time domain is implies multiplication by s in Laplace transform domain. Similarly, we can show that Laplace transform of d square by dt square of f of t is equal to s square into f of s minus s into f of 0 minus f dash 0. Here, no, please note that f of 0 is value of f of t at t is equal to 0 and f dash 0 is value of f dash t at t is equal to 0. Now, let us look into another property, that is integration in time domain. From this, Laplace transform of integral 0 to t f of u du is equal to 1 by s multiplied by f of s. Similarly, Laplace transform of integral minus infinity to t f of u du is equal to 1 by s into f of s plus 1 by s multiplied by integral minus infinity to 0 f of u du. So depending on the limits of the direct integral, we see that the result of the Laplace transform of the integral of a function changes. So from this we can say that Laplace transform of integral 0 to t f of u du is equal to 1 by s into f of s. Laplace transform of integral minus infinity to t f of u du is equal to 1 by s into f of s plus 1 by s multiplied by integral minus infinity to 0 f of u du. Now let us look into another property of Laplace transform, that is integration in frequency domain. From this we can, as a part of this property, we can show that Laplace transform of t into f of t is equal to minus 1 multiplied by d by ds of f of s. So extending this to a generic multiplication of t power n to the f of t, we can show that Laplace transform of t power n into f of t is equal to minus 1 whole power n dn by dsn of f of s. From this we can show that differentiation in the Laplace transform domain is equivalent to multiplication by t in time domain, or nth derivative in the Laplace transform domain is equivalent to multiplication by t power n to the f of t in time domain. Now let us look into another property, that is integration in frequency domain. As a part of this, we can show that Laplace transform of 1 by t into f of t is equal to integral s to infinity f of s ds. That is, division by t in time domain is equal to integration in the frequency domain, but over the limits from s to infinity. Now let us consider initial value theorem, as per which the initial value of a function f of t, that is f of 0, can be found from f of s. So the initial value theorem is given as limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s. Please note that this theorem applies to only those rational function f of s where the order of the numerator polynomial is less than the order of the denominator polynomial. So, for example, if we take f of s is equal to s plus 1 divided by s square plus 3s plus 2, here we see that the order of the numerator polynomial is 1 and the order of the denominator polynomial is 2. So from this we can say that here the initial value theorem can be applied. So if we take another example where f of s is equal to s plus 1 divided by s plus 5. Here, the order of the numerator polynomial is 1 and the order of the denominator polynomial is also 1. As the given condition is not satisfied here, we can say that the initial value theorem cannot be applied here. So, from this, we can say that the initial value theorem can be applied only if the order of the numerator polynomial is less than the order of the denominator polynomial. Now, let us look into another theorem called final value theorem. So, as the theorem says, using the final value theorem, we can find the value of f of t as t tends to infinity. Using the final value theorem, and the final value theorem is as shown. That is, limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. So here please note that given any function f of t whose Laplace transform is f of s, the final value of f of t, that is limit t tends to infinity f of t, can be found as limit s tends to 0 s into f of s using f of s. Also please note that for finding the for applying the final value theorem to any function f of t, the necessary condition is that the poles of s into f of s should be strictly on LHS of S plane. That is, the poles of the rational function s into f of s should be strictly on the LHS of the S plane. If the poles lie on the RH side or on the j omega axis, final value theorem cannot be applied. So if we take an example of f of s is equal to 1 by s square plus 3, please note that here the final value theorem cannot be applied because of the reason that the poles are equal to plus or minus root 3j and they lie on the j omega axis. Also, if we take another function f of s is equal to 1 by s plus 3, here we see that the poles lie on the LHS of s plane strictly. So the final value theorem can be applied here. Now let us consider another theorem which is let us consider another property which is related to convolution. So as per this, we know Laplace transform of f1 of t convolved with f2 of t is equal to f1 of s multiplied by f2 of s. That is, convolution in time domain is equal to multiplication in frequency domain. Similarly, Laplace transform of f1 of t multiplied by f2 of t is equal to f1 of s convolved with f2 of s. Please note that the multiplication in time domain is equivalent to convolution in frequency domain. From this we can say that multiplication in time domain is equal to convolution in frequency domain and vice versa. Here, whenever I said frequency domain, please note that I am implying the Laplace transform domain. Now, let us look into another formula that is related to Laplace transform of a periodic function. If there is a signal f of t which is periodic with a period capital T, Laplace transform of f of t can be written as 1 by 1 minus e power minus st multiplied by f1 of s, where f1 of s is equal to integral 0 to t e power minus st f of t dt. So if there is a signal f of t with a period capital T, Laplace transform of f of t is given as 1 by 1 minus e power minus st multiplied by f1 of s, where f1 of s is equal to Laplace transform of one period of f of t. Now let us start looking into Laplace transform of some of the standard functions. First, we will find the Laplace transform of unit step function. We know that unit step function u of t is equal to 1 for t greater than or equal to 0, and it is equal to 0 otherwise. So from this we can write that Laplace transform of u of t is equal to integral 0 to infinity 1 multiplied by e power minus st dt. We know that integral of e power minus st is e power minus st divided by minus s, and the limits are infinity and 0. We see that upon substituting the limits, it is minus 1 by s multiplied by limit t tends to infinity e power minus st minus limit t tends to 0 e power minus st. We know that as t tends to infinity, limit t tends to as t tends to infinity e power minus st is 0, and as t tends to infinity 0 e power minus st is equal to 1. So from this can be simplified as minus 1 by s multiplied by minus 1, which is equal to 1 by s. From this we can write that Laplace transform of unit step function, that is u of t, is equal to 1 by s. Now we will find the Laplace transform of t into u of t. So here also, using the analysis formula, we can show that this is equal to 1 by s square. More generically, if n belongs to z plus, that is if n is a positive integer, Laplace transform of t power n multiplied by u of t is equal to factorial n by Sn plus 1. So we see that if n is equal to 1, Laplace transform of t power n into u of t boils down to Laplace transform of t into u of t. So the first one is a special case of Laplace transform of t power n into u of t. Now let us find Laplace transform of sine omega t multiplied by u of t. We know that sine omega t is equal to e power j omega t minus e power minus j omega t divided by 2j. So from this we can write that Laplace transform of sine omega t ut is equal to Laplace transform of e power j omega t minus e power minus j omega t divided by 2j multiplied by u of t. This can further be simplified as 1 by 2j multiplied by Laplace transform of e power j omega t u of t minus Laplace transform of e power minus j omega t u of t. We know that Laplace transform of e power at f of t is equal to f of s minus a. This is a theorem that we covered before. From this we can say that Laplace transform of e power j omega t u of t is equal to 1 by s minus j omega, as Laplace transform of u of t is 1 by s. So from this we can write that Laplace transform of sin omega t ut is equal to 1 by 2j multiplied by 1 by s minus j omega minus 1 by s plus j omega. This upon simplification becomes omega divided by s square plus omega square. So from this we can say that Laplace transform of sin omega t ut is equal to omega by s square plus omega, omega by s square plus omega square. Similarly, we can prove that Laplace transform of cos omega t ut is equal to s divided by s square plus omega square. For proving the same, we can use the property that cos omega t is equal to e power j omega t minus e power minus j plus e power minus j omega t divided by 2. By using this property, or by using the thing that cos omega t is equal to e power j omega t plus e power minus j omega t divided by 2, we can show that Laplace transform of cos omega t ut is equal to s by s square plus omega square. Now we need to find the Laplace transform of e power at multiplied by u of t. We know that Laplace transform of u of t is equal to 1 by s, and we also know that Laplace transform of e power at multiplied by f of t is equal to f of s minus a, where f of s is the Laplace transform of f of t. Using these two properties, we can say that Laplace transform of e power at u of t is obtained by replacing s by s minus a in Laplace transform of u of t. From this, we can say that Laplace transform of e power at u of t is equal to 1 by s minus a. Similarly, we need to find out Laplace transform of e power at multiplied by cos omega t u of t. We know that Laplace transform of cos omega t u of t is equal to s by s square plus omega square. From this, the Laplace transform of e power at cos omega t ut can be found out by replacing s by s minus a in Laplace transform of cos omega t ut. So Laplace transform of e power at cos omega t ut is equal to s minus a divided by s minus a whole square plus omega square. Similarly, we can show that Laplace transform of e power at sin omega t ut is equal to omega divided by s minus a whole square plus omega square. Now we need to find out Laplace transform of cos h omega t u of t. We know that cos h omega t is equal to e power omega t plus e power minus omega t divided by 2. So from this, we can show that Laplace transform of cos h omega t u of t is equal to half multiplied by Laplace transform of e power omega t u of t plus Laplace transform of e power minus omega t u of t. We know that Laplace transform of e power omega t u of t is equal to 1 by s minus omega. We can also show that Laplace transform of e power minus omega t u of t is equal to 1 by s plus omega. Upon substitution, we get that half 1 by s minus omega plus 1 by s plus omega. Upon simplification, this is equal to s by s square minus omega square. From this, we can say that the Laplace transform of cos h omega t u of t is equal to s by s square minus omega square. Similarly, we can show that Laplace transform of sin h omega t u of t is equal to omega divided by s square minus omega square. This is by substituting sin h omega t. Sorry, this can be obtained by substituting sin h omega t as e power omega t minus e power minus omega t divided by 2. Now let us look into Laplace transform of some of the standard functions. That is, Laplace transform of root t u of t is equal to root pi divided by 2 into s power 3 by 2, and Laplace transform of t power minus 1 by 2 u of t is equal to square root of pi by s. So till now we looked into the analysis formula of the Laplace transform. We looked into properties of Laplace transform. Also, we looked into Laplace transform of some of the standard functions. So now we will look into another topic which mainly talks about the way in which we can find the Laplace transform of any generic one-sided function f of t. So we can find Laplace transform of any generic one-sided function f of t by using analysis formula, that is Laplace transform of f of t is equal to integral 0 to infinity e power minus st f of t, or by using properties of Laplace transform which we looked into already, or we can also find the same by inspection, because the f of t given may be of any standard form. So using the Laplace transform of some of the standard function, we can find Laplace transform of f of t. So from this we can say that we can find Laplace transform of f of t by analysis formula, or properties of Laplace transform, or by inspection. Now let us solve some problems as related to finding the Laplace transform of one-sided signals. So the first problem is find Laplace transform of e power 3 into t minus 1 multiplied by u of t minus 1. We know that Laplace transform of e power minus 3 into u of t is equal to 1 by s plus 3. We also know that Laplace transform of f of t minus a is equal to, sorry, f of t minus a multiplied by u of t minus a is equal to e power minus as into f of s. It means that delaying by a in time domain is equivalent to multiplying by e power minus as in Laplace transform domain. From this we can write that Laplace transform of e power minus 3 into t minus 1 u of t minus 1 is equal to e power minus s multiplied by 1 by s plus 3. Now let us consider another problem in which it is given that there is a function h of t which is equal to delta of t minus delta of t minus capital T. There is another function g of t which is equal to delta of t minus delta of t minus 2t. We need to find Laplace transform of h of t convolved with g of t. We know that from the properties of Laplace transform, this is equal to Laplace transform h of t multiplied by a Laplace transform of g of t. We know that Laplace transform of h of t is equal to 1 minus e power minus st. We also know that Laplace transform of g of t is equal to 1 minus e power minus 2st. From this we can write that Laplace transform of h of t convolved with g of t is equal to 1 minus e power minus st multiplied by 1 minus e power minus 2st. In case we need to find h of t convolved with g of t, we can find the same by finding the inverse Laplace transform of the result that we obtained, which can be written as L inverse of 1 minus e power minus st minus e power minus 2st plus e power minus 3st. We know that L inverse of 1 is delta of t. We also know that L inverse of e power minus st is equal to delta of t minus capital T. L inverse of e power minus 2st is equal to delta of t minus 2 capital T, and L inverse of e power minus 3st is equal to delta of t minus 3t. So for the given h of t and g of t, we were to find Laplace transform of h of t and g of t, which is obtained as 1 minus e power minus st multiplied by 1 minus e power minus 2st. We also found h of t convolved with g of t in addition, which is obtained as delta of t minus capital T minus delta of t minus 2t plus delta of t minus 3t. Now let us consider a periodic function f of t, which is as shown in the figure. Please note that the periodic function is an impulse train, and the signal f of t is periodic with a period t. We need to find Laplace transform of f of t. We know that Laplace transform of a periodic function f of t can be written as 1 by 1 minus e power minus st multiplied by f1 of s, where f1 of s is equal to integral 0 to t e power minus st f of t. But we know that the given signal f of t is equal to sigma k equal to minus infinity to plus infinity delta of t minus kt. That is, the given periodic function f of t is an impulse train at an interval of capital T. So from this, we can say that for each period t, there will only be one impulse. So from this, we can write that f1 of s is equal to integral 0 to t e power minus st into delta of t, because in the first period there is only one impulse, which is at t equal to 0. From this we can say that this impulse boils down to 1. From this, the Laplace transform of the periodic impulse train given, which is periodic with a period capital T, is 1 by 1 minus e power minus s t. So the Laplace transform of the impulse train, which is periodic with a period capital T, is 1 by 1 minus e power minus s